So as of now in chapter 5 we have discussed the Newton's first, second and third law, the free body diagram, the contact forces and one-dimensional system where we consider forces in one dimension. Now we'll consider the forces in two dimensions. And from the Newton's second law, we understood that the object's acceleration is equals to net force acting on it divided by its mass. Now, if the forces are acting in more than one direction, then its acceleration is in the direction of the vector sum of the forces. Let's take an example to understand this. So here we have two astronauts pushing the 940 kg satellite, and the astronaut 1 pushes with a force of 26 Newton along the positive x, and the astronaut 2 pushes with a force of 41 Newton at an angle 52 degrees above the x-axis. Now, can you figure out the direction and the magnitude of satellite's acceleration? Yes, we can. We can find it by calculating ax and ay components of acceleration separately and then combining these components to find the acceleration and its direction. So first, let us make the free body diagram. So I have drawn the free body diagram and also the coordinate system. Now you may see that the F2 force have a component in the horizontal direction and in the vertical direction. So let us find the component. So this is the force F2 and this angle with the x-axis is 52 degrees. So its x component is this one, and this is F2x, which is equals to F2 cosine theta. Theta we have 52 degrees, and the vertical component we have this one. This is F2y, and this is we have F2 sine theta, and theta we have 52 degrees. Now we're going to use the Newton's second law of motion in x and y direction separately. So in the x direction we have F1 force, which is equals to 26 Newton. This is along the x direction, so this we can write F1x. Then F2x, the component of force in the x direction, we have F2 cosine 52 degrees. So F2 we have 41 cosine 52 degrees. So we have only these two forces in the x direction. So the net forces in the x direction, that is sigma fx, this would be 26 Newton plus 41 cosine 52 degrees, which is equals to 51 Newton. Now according to the Newton's second law of motion, the acceleration in the x direction, this would be sigma fx divided by the mass of the body. So sigma fx we have 51 Newton, and mass for the satellite is 940 kgs. So this would be 940 kgs, and on solving we'll get the acceleration of the satellite along the x direction to be 0.054 meter per second squared. Now similarly we can apply the Newton's second law in the y direction to find its acceleration in the y direction. We have F1y, that is component of the first force in the y direction is 0, because F1y is along the x, so its component in the y direction will be 0. Then F2y, component of the second force in the y direction, this would be F2 sine 52 degrees, right? So sigma Fy, we have only F2 sine 52 degrees, which is equals to F2 we have 41, then sine 52 degrees. Now the acceleration in the y direction, this would be equals to, now this value comes out to be as 32 Newton. So Ay would be sigma Fy divided by the mass. Sigma Fy we have 32 Newton divided by mass is 940 kgs. So the acceleration of the satellite along the y direction is 0.034 meter per second squared. So we have found the components of acceleration in the x and y direction. So what would be the acceleration, the total acceleration? This would be under root ax square plus ay square is equals to under root x component we have 0.054. So 0.054 and its whole square, plus y component we have 0.034 and its whole square. So on solving, we'll get the acceleration to be 0.064 meter per second squared. So this would be your acceleration. Now its direction, that is the theta. This theta would be tangent inverse the y component over the x component. So tangent inverse the y component we have 0.034, x component we have 0.054, and on solving we'll get the angle to be 32 degrees, and this is above x-axis, and this direction is same as the direction of net force on the satellite. Let me represent this on the figure first. So F1 force was along this direction, this is F1, and this was F2, right? Now the net force would be along this direction, this one. From the concepts that we studied in our vector addition, this would be F net, and this angle would be same, that is 32 degrees that we calculate here. Now let us take a couple of more examples to understand it better. So in this example, we have a camper lifts a food cooler with a weight of 192 Newton by using two ropes. Now rope 1 exerts a force of magnitude 166 Newton at an angle 47.4 degrees above horizontal, that you can see in this image. Now rope 2 exerts a force F2 at an angle 36.1 degrees above horizontal. Now there are two parts in this question that we need to solve. In the A part, we need to find the force F2 that produces a net force on the cooler that is straight upwards. So net force on the cooler is acting in the upward direction. Okay. Now first what I'm going to do is I'm going to make the free body diagram, and for that we can consider this object to be a point mass object. So this is point mass. Now the weight force is along the downward direction, this is W. F2 force is along this direction, this is F2, and this angle we are given to be 36.1 degrees. Then F1 is along this direction, this is F1. So and this angle we have 47.4 degrees, right? And this direction I'll be taking the X, and this one is the Y direction. Now the force F2 will have its component along the X and the Y direction. This is force F2, and this angle we have 36.1 degrees. Now along the X direction, its component will be F2 cosine theta, theta is 36.1 degrees, and along the Y direction its component will be F2 sine theta, theta we have 36.1 degrees. Now F1 force also have component along the X and the Y direction, so this is our force F1, and this angle we have 47.4 degrees. Now along the Y direction we have F1 sine theta, theta we have 47.4 degrees. Now this would be along the negative X direction, this component, and this would be minus F1 cosine theta, theta we have 47.4 degrees. Now to find the magnitude of force F2, I'm going to apply the Newton's second law of motion along the X direction. Now we know that the net force acting on the object is along the Y direction, and along the X direction the net force is 0. So we can write that sigma Fx, this should be equals to 0. And in the X direction we have only two forces, this one and this one. So sum of these two forces should be equals to 0. So we can write that F2 cosine 36.1 degrees minus F1 cosine 47.4 degrees, that should be equals to 0. Now F1 we are already given in the equation to be 166 Newton, so we can put it here. F2 cosine 36.1 minus F1 we have 166 Newton cosine 47.4 degrees is equals to 0. Now from here the F2 force, this would be equals to 166 cosine 47.4 divided by cosine 36.1, which is equals to 139 Newton. Thus, the magnitude of the force F2 is 139 Newton. So this was the answer for the A part. Now next we can solve the B part, where we need to find the net force acting on the cooler given F2 has a magnitude determined in part A. So the net force we have to find. Okay. Now in the y direction, the net force would be sigma Fy. This would be equals to, we have three forces in the y direction. One is this W, then two, this one and this one. So we can write F net along the y direction. This would be F1 sine 47.4 degrees, then plus F2 sine 36.1 degrees. Then W is along the negative y, so we can write this is as minus W. Now we can put the values to find the net forces along the y direction. So this is F1. F1 we have 166, so 166 sine 47.4. F2 we have 139 sine 36.1 minus W. W we have 192, so 192 Newton. Now on solving the net forces along the y direction, we have 11.9 Newton. Now the net force along the x direction, we know it is equals to 0, that we saw in the A part. So the net forces on the object, this would be equals to its y component plus the x component. X component we have 0, so y component we have 11.9 Newton, and in vector form we can write this will be y cap. This is in the vector form. So this would be the answer for the B part. Now I'll be taking one more problem on this topic. So in this example, we have a sled that have a mass of 4.60 kgs, and the force acting on the sled has a magnitude of 6.20 Newton, and it points at an angle 35 degrees above horizontal. Now the sled starts at rest, so its initial speed we have 0. Now we need to find how fast it is moving after being pulled for 1.15 seconds. Okay, so the only force acting on the sled is this force F that has a magnitude of 6.20 Newton. So along the x direction, its component will be F cosine theta. F is 6.20 cosine theta, we have 35 degrees. So on solving, we'll get this Fx to be 5.08 Newton. Now from the Newton's second law of motion, we can write that sigma Fx is mass times the acceleration of object along the x direction. Now from here, Ax, this would be sigma Fx divided by the mass. Now the net forces along the x direction is only this force Fx, so we can write Fx divided by the mass. So Fx we have 5.08 Newton divided by mass is 4.60. So with this, the acceleration is 1.10 meter per second squared. Now we're going to use the kinematic equations that we studied in chapter 2 and 4. So Vx is equals to V naught x plus Ax times t. Now initial speed is 0, so this term is 0. Acceleration in the x direction we have 1.10, so we can write 1.10 meter per second squared, and time we have to take it to be 1.15 seconds. So 1.15 seconds. So on solving, the speed at this instant will be 1.27 meter per second.